Math 2415, Chapter 10, Vectors and the Geometry of Space. Section 2, Vectors. Video 1, Vectors as Arrows. Many of you have seen vectors before. I know this because earlier today I walked by a physics class where you were talking about vectors. It was quite fascinating. But for our purposes, this is going to be an introduction to vectors. And by a vector, I mean a quantity with magnitude and direction, which is actually the physics and engineering definition of a vector. Excuse me. In other fields, vectors are defined differently. For example, in computer science, a vector is defined as an array of numbers. Whereas from a theoretical math perspective, a vector is simply an object with certain properties. But for the purposes of this course and for the physicists and engineers amongst you, we're going to view a vector as a quantity with magnitude and direction. Now, how we represent that vector, there's a couple of ways that we're going to do it. The most standard visual way is to just draw an arrow pointing in a certain direction with a certain magnitude or a certain length. What makes two vectors equal? If they have the same magnitude and the same length. So imagine picking up this vector rigidly without changing its direction and moving it down here somewhere. It's not quite the same direction and magnitude, but just pretend that it is. And then we would have the same vector. When you have a vector represented as an arrow, it has what's called an initial point and a terminal point. The initial point is the point from which the arrow initiates. So this would be our initial point. And the terminal point is the point at which the vector arrow terminates or ends. So we could also uniquely define a vector. Well, we could define a vector by identifying a terminal point, an initial point, and a terminal point. I almost said uniquely, but that's not the case, as we'll see here in a moment. If we want to represent a vector in R2, which just means two-dimensional space, so a plane, if you will, then we can represent a vector by simply picking 2 points and connecting them. For example, let's say that we picked an initial point of 1, 2. Let's make it 1, 3. And we wanted to connect it to the point 4, 5, which is about here. Then we could form a vector by using 1, 3 as the initial point and drawing an arrow to 4, 5. And just for kicks, let's call this vector v. Now, variable-wise, the way that you typically represent a vector is to write a single case lower letter in bold font. Since I can't write in bold on the board, I'm going to choose to draw an arrow over it and say that that is vector v. Now, another way to write a vector is to name the initial and terminal points. For example, if I call this point A and this point B, then we can say that this vector is equal to AB by explicitly referring to the initial and terminal points that we use to locate the vector. However, that is not the only location of vector v. Any vector that has the same direction and the same magnitude would be the same as vector v. For example, if we started at the origin, so we'll call that capital O, whose coordinates clearly are 0, 0, and then as an initial point, and as a terminal point, we use the point 3, 2, and connected them. It may not be immediately obvious, but those vectors have the same magnitude and the same direction. We could check it easily using some algebra. For the same magnitude, we could use the distance formula on these 2 points and get the square root of 13. And if we did the distance formula on these 2 points, we would also get the square root of 13. And so they have the same length or the same magnitude. As far as the direction, we can calculate the slope of each of these as parts of a line. The slope of each of these would be 2/3, meaning that they're going in the same direction. If we call this terminal point C, just because it's the next letter in the alphabet, then all 3 of these vectors are equal because all 3 of them have the same direction and magnitude. A vector is not uniquely determined by an initial point and a terminal point. There can be different initial points and different terminal points to define a vector, but as long as the magnitude and the direction are the same, they are the same vector. It's the same thing in R3. which I'm going to illustrate by changing this 2 to a 3. So R3 is another way of saying three-dimensional space. And I'm going to add third axis. Technically speaking, this third axis should be perpendicular to the board and literally project outward like this, but I can't draw it out in space. So I'm going to draw that third axis by drawing a diagonal line here and imagining that it's coming out and then marking it off a little bit. As we discussed in class previously, when you're representing three-dimensional space, this axis protruding out is the x-axis, the horizontal axis is the y-axis, and this vertical axis becomes the z-axis. And we can do the same thing to represent a vector in 3 dimensions by simply connecting 2 points. One is the initial, one is the terminal. For example, let's say I took the point 2, 3, and -1, so about here. 2, 3, -1. And then I took the point 1, -2, +4. And again, I'm just tracing along each axis as I call out each number, and then connect them. By the way, it matters which one is the initial point and the terminal point, because if I reverse them, I change the direction. And we'll call this vector W just because I called the other one V. That would be a vector in 3 dimensions. And again, the vector is determined by its direction and its magnitude, not necessarily its initial point and its terminal point, because I can pick up this vector, move it around without changing its direction, put it somewhere else at a different initial and terminal point, but still have the exact same vector. In the next video, we'll discuss what it means to add vectors and to do scalar multiplication with vectors using arrows. Gotta go this way.